This is Advanced Algebra Lessons 2.1 and 2.2. They will be covering direct and inverse variations. To start with, we will be looking at direct variation equations and functions. A direct variation equation is one in which one variable is a multiple of another variable or product of variables. And a direct variation function is a function that can be described by a formula in the form of y equals k times x to the power of n. K is not equal to 0 and n is greater than 0. When we use direct variation and inverse variation for that matter, we have a k, and that is considered our constant of the variation. So in words, y varies directly as x to the power of n, or y is directly proportional to x to the power of n. In direct variation, both quantities increase or decrease together. This is very important. You'll want to make note of this on your note packet. I'm going to talk about direct variation by using the area formula for a circle. The area formula is A equals pi times r squared. So area varies directly as the radius squared. In this situation, we're using the formula, and our value for n is 2, right here. That's our power. K is pi, that's our constant. R is our independent variable, and A is our dependent variable. I would like to work through our first variation problem together. We're going to look at the surface area of a cube. The surface area S of a cube is directly proportional to the square of the length E of an edge. The first thing I want you to do is identify the dependent and independent variables and write an equation relating them. When we read the sentence again, the surface area S of a cube is directly proportional to the square of the length E of an edge. So directly proportional says I'm going to multiply my products, my constant and my independent variable. So S is my dependent variable equals K times E to the power of 2, since they said it's directly proportional to the square of the length E of an edge. So E is our independent, S is our dependent. In part B, we're going to look at some information and try and determine our constant of variation K. A cube with edge length of 5 centimeters has a surface area of 150 square centimeters. Determine the constant of variation K. So when we do this, we start with our equation that we formed from up above, S equals K times E squared, and we insert some values. We have E being 5 centimeters, since they say that's the edge length, so we insert 5 in place of E, so 5 squared is part of our formula. And it has a surface area of 150 square centimeters, so we're inserting 150 in place of S. And then we can go ahead and solve our equation for K. K equals 6. So part C then says we want to rewrite the variation equation using our result from part B. So in doing so, we found K, so we just plugged in 6 in place of K. So our new equation is S equals 6 times E squared. And now our final question. What is the surface area of a cube with edge length of 8 centimeters? So now we're going to take our new equation that's specific to our problem, and we're going to insert 8 in place of E. So S is going to equal 6 times 8 squared. So S is going to equal 384 centimeters squared. As we worked through this example in parts A, B, C, and D, we actually followed the procedure for solving variation problems. The first step, 1, write the general variation formula. Second, use the formula to find K. Third, write the formula with the value of K in it. And 4, use the formula to answer the question. We will be using this procedure for solving variation problems in both direct and inverse variations. I'd like you to stop the video at this time and work through the next example, example 2, at the bottom of your page. Let's see how you did with example 2. First question, write an equation with variables m, p, and k that describes the variation. Suppose m varies directly as the fifth power of p. If m equals 96 when p equals 2, find m when p equals 5. So in order to answer number 1, m is varying directly as the fifth power of p. So that would be written m equals k times p to the power of 5. Part 2, we then substitute the various variables, or we substitute 96 and 2 in place of our variables in order to solve for k. So we take 96 equals k times 2 to the fifth and solve for k, and we get k equaling 3. In part 3 then, we rewrite the formula with the value of k. So that looks like m equals 3. We inserted 3 in place of k, times p to the fifth. And then the fourth question, or the fourth piece, is to solve for m if you know that p is equal to 5. So we're inserting now 5 in place of p, so 3 times 5 to the fifth is equal to 9,375. So m is 9,375. So when we worked through this, the first part was our general equation. Second part, we used the information given to us to find our value for k. Our third part was to write a specific equation using our value for k, and then answer the question is our fourth part. In the second half of this video, I would like to look at inverse variation, and specifically inverse variation functions. That is a function that can be described by a formula in the form of y equals k divided by x to the power of n. Like direct variation functions, k is still not equal to 0 and n is greater than 0. K is still our constant of variation. In words though, this time, instead of saying directly, we say inversely. Y varies inversely as x to the power of n, or y is inversely proportional to x to the power of n. In inverse variation, as either quantity increases, the other decreases. So once again, we pointed out in direct variation that this piece is important. Same thing in inverse variation. We're going to take a look at a formula that was presented to you in your reading on page 79. It was dealing with workers and time, and they gave us a formula stating that t was equal to 48 divided by w. In this situation, t varies inversely as w. Here, our power of n is 1, even though we don't see it. K is 48, so 48 is the constant of variation. Here, w is the independent variable, and t is the dependent variable. Let's just work through example 1 together. The number of units u in a length varies inversely with the length L of the unit. Write an equation that expresses this relationship. So once again, the unit u is a length that varies inversely. So we know inversely, we know we're going to divide. So k is going to be over our independent variable, which will be L. And it does not say it's to a certain power, so we can assume it's to the power of 1. So our equation would be u equals k over over L. In example 2, it comes directly from your reading on page 80. According to the law of the lever, in order to balance the seesaw, another person must sit a certain distance from the pivot of a seesaw, and that distance is inversely proportional to his or her weight w. Algebraically, d equals k over w. Now we're going to do a problem that is similar to the one that you did in your reading. I've taken the picture from that problem, but I've adapted it to this new problem. Ashley and Sam are trying to balance on a seesaw. Suppose Sam weighs 34 kilograms and is 1.8 meters from the pivot. If Ashley weighs 38 kilograms, how far from the pivot should she sit to balance Sam? We're going to follow the same four-step process that we used with the direct variation. So first we need to write a variation equation relating d and w from the law of the lever. So that was d equals k over w. Next we need to find k, so we're going to substitute Sam's weight in place of W, and the distance from the pivot into our equation D equals K over W. So that becomes 1.8 meters equaling K over 34 kilograms. We then go ahead and solve for K by multiplying both sides by 34. So that gives me K equaling 1.8 meters times 34 kilograms, which ends up being 61.2 meter kilograms. We now substitute our value for K into the formula. So that's our third step. And you can see we've substituted down here D equals 61.2 over W. And so now we can go ahead and answer the last question, or the main question that we were trying to from the beginning. If Ashley weighs 38 kilograms, how far from the pivot should she sit to balance Sam? So we substitute Ashley's weight into the formula above to find the distance she must sit from the pivot. So 61.2 is our value for K. Her weight was 38 kilograms. So D, the distance from the pivot, would be 1.6 meters. I would like you to stop the video at this time, try example 3, and start the video when you are ready, and we will discuss your findings. The formula from example 3 comes from page 82 in your reading. The intensity I of light is inversely proportional to the square of the distance D from the light source. So I equals K over D squared. So I want you to suppose the intensity of light 6 meters from the light source is 30 lumens. Find the constant of variation and determine the intensity of the same light 9 meters from the source. So our equation was listed here, I equals K over D squared. So we substitute the information given to us. The light source is, it's 6 meters from the light source, so that's 6 squared on the bottom, and it is 30 lumens. That's our intensity. So we solve for K. 6 squared times 30 is 1080. So K represents 1080. So I equals 1080 over D squared. So now we're going to insert the distance 9 meters from the source. So 1080 divided by 9 squared is going to be 40 over 3, which is approximately 13.3 lumens. This now concludes lessons 2.1 and 2.2.